So we will extensively talk about stress versus strain. And what that simply means is that if you have a given material, and if you apply a force onto that material, the material will deform, right? And the stress is, we will see again, defined as the force over the surface area. And the strain will be the rate of the deformation of the material. So if you have a given material, this stress-strain curve will look somehow similar to this curve that is shown here. The details may vary between materials. But what most of the materials, or many of the materials, do have in common is this linear behavior at relatively small stresses. So, for example, and this is so-called elastic behavior. So this is indicated on the left-hand side from this point P, the material goes through linear behavior. What that means is that if I take a piece of a material, and if I apply very small force or stress, the material will deform, and the deformation will be proportional to the applied stress, right? And how much it deforms depends on the specifics of the material. However, if the stress itself is larger, or if, again, the threshold depends on the material, if this stress is larger, the material will plastically deform, right? So again, we will talk about details about what it means elastically and plastically deformed. But again, the fact that the material plastically deforms, the question is, what is this threshold? Where does it happen, and why does it happen? So we will see that this plastic deformation is closely related to the introduction or to the formation of dislocations in these materials. Okay? And again, just remember, elastic behavior is the one where the strain or the deformation of the material is proportional to the stress applied, and usually it's reversible. Okay? So, again, we will talk about yield strength, or this is the threshold where this plastic behavior happens, or that is defined where the material is deformed by 0.2%. It's a question of the definition, but this will be one of the important parameters that we will talk about, but it's called yield strength. Okay. So let's define what we mean by elastic and plastic deformation, again, because we will use these concepts extensively. So if you have a crystal, right, so this is your initial crystal, this is the material itself, and if you zoom in, you will see a set of atoms that are arranged in the crystal lattice. So if I apply a small load, right, so if I apply a force, the material will be slightly elongated by a value of delta. So what that means that if the deformation is elastic, the bonds will simply stretch a little bit. But the deformation will be relatively small, such that this deformation is reversible, meaning that if I unload, or when I release the force or the stress, the atoms will return to the normal. So this is so-called elastic behavior. Again, the deformation is proportional to the force, or again, if it's linear, but it is reversible. So what the elastic means is that it is reversible. And if I look at the force as a function, or the strain as a function of the force that I apply, then this, oh gosh, what's happening? So what that means is that if I go in one direction, and if I go in the opposite direction, I will return to the same spot. Okay, so we will have to restart this, and I apologize for this. Okay, so again, what elastic behavior means is that if you have a deformation of the material as a function of the force, if you go in the one direction, if this is linear, so the deformation will be proportional to the applied stress, and if you release the stress, you will end up in the same point. This again can be nonlinear, but the main point behind the elastic is that one is reversed, so the process is reversible. Okay, so let me just try this once more. So this was the elastic behavior, right? So the question is, what does it mean that the material plastically deforms, right? So if I permanently change the shape of the material, what does it mean? So the plastic deformation is permanent. And again, what that means is that if you have the initial crystal, if you apply a force, for example, you just pull out the material or you try to deform it in a different way, the material will be deformed And the magnitude of the deformation will be the elastic component plus the plastic deformation. Again, the elastic component will be the component of the deformation that will relax after you relax the force. And the plastic component will be the one that remains in the material. And when you release or unload, then the final deformation will be the plastic component. So when I plot this as a deformation as a function of force, this would look like this. So the material would go through an elastic phase, then it would go through this plastic deformation, and if I release the stress or the force, the material will go down and there will be a permanent deformation, which is the delta plastic. Okay? And we will see that this happens by shearing the planes within the crystal. What that means is that the planes themselves within the crystal will physically move inside of the material. Yes?
Can we predict where the dislocations occur?
Excellent question. The question was whether we can predict where the dislocations will occur. Did you think about specific material, or if you have a given material, where in the material it will be? So you can predict what will be the planes and what will be the directions in which the dislocations will be formed. And we will learn this as we go throughout. I think this will be covered in the next lecture. But if you have a given material, you can predict which of the planes will be sheared. And this doesn't necessarily have to be either parallel or perpendicular to the force. There is a relationship that if you know what is the direction of the stress that you're applying, you can calculate which direction in the plane is most likely to shear. And that's the power of mechanics. If you understand these details, you can predict and tailor the materials to formulate that. Okay, so there will be a couple of different types of stresses and strains that we will talk about, and I would just like to define them so when we talk about them, you know what we're talking about. So the tensile stress and the strain simply mean that you're applying basically, if you're applying a force in this direction, and if this was the area, then the stress itself would be the force over the areas of the material, right? So this is called a tensile stress. And if you have a shear stress, tau, if, for example, you have a component of if the force is acting not necessarily along the elongation of the material, it will have two components. It will have the tensile component, and it will have the shear component of the force. And the shear stress tau is then defined as the Fs over area of the material A0. And again, the Fs is the force that is acting in the shear direction in this material. I can ask you a question, what are the units of the stress? Pressure. So what's the unit of the pressure? Pascal. It's simply Newton over meter squared, which is Pascal. So the stress itself, it has the units of the pressure, but again, it's the force that is normalized to the surface or the area of the material that you're talking about. So equally, when we talk about the tensile and shear strain, so we are trying to define how the material deforms. So the stress will tell you about the magnitude of the force that you're applying to the material, and the strain will tell you about the magnitude of the deformation itself. So the tensile strain will be defined as epsilon is equal delta over L. Again, here we are applying the force in the tensile direction, and the change of the length of the material relatively to the initial length of the material is defined as a tensile strain. And again, this is just simply illustrated here that in 3 dimensions you're simply taking a piece of a material and pulling it along the axis of the material itself, and this would be then the tensile strain. And the lateral strain would be epsilon L is equal as minus delta L over the width of the material. Again, this is the change in the lateral direction normalized to the diameter of the material, which is here. So then the shear strain will be the strain or the deformation of the material if you apply a shear stress. So if you apply a force in this particular direction, so you're shearing the material, And in this particular case, the shearing strain, which we'll use extensively, is called gamma. It will be the difference, or this deformation of the material, delta x, over the height of the material, over y, which is actually, if this is the angle theta, this would be the tangent of this angle here. So if the material permanently, or if it deforms in this particular way, if you can measure this angle, you're simply taking the tangent, and this would be the shear strain. So again, I can ask you a question, what are the units of strain? It's unitless, right? Okay. So we will come back to this particular picture and we will try to understand details, right? So I told you about the elastic and the plastic deformation. Again, let me remind you is that the elastic deformation is in this particular part of the graph, where again, the deformation is reversible. And again, the slope of this graph here simply depends on what is the strength of the bonds within the material. So if you have two atoms within the material and the bond is very strong, then this deformation will be relatively small, and the slope of this curve will look somehow like this. So it would be steeper, right? So for the same stress, I'm applying the same force, but the material is deforming by a smaller amount. And what that simply means is that you're following the curve, or you're following the this slope of the bonding energy in the material. So in principle, this part of the curve is relatively well understood, and you can somehow predict how the material will behave if you know what type of bonding you exist in the materials, right? So, for example, if you have ionic materials or metals, the deformation or the elastic part of the curve will be very different. So the question is then, what happens in this plastic regime, and can you predict where this will happen? Can you predict where this plastic deformation will happen for a given material? So we will actually do this right now. So what we are trying to understand is, if you have a material, if this is a crystalline material, if you apply a shear stress to the material, if the material is elastically deformed, when you release the stress, you're simply going in between these two positions. So the atoms are slightly moving their position, but you release the stress, and they will return and they will relax to their equilibrium position. The plastic deformation, what that physically happens within the material, is that you physically move one part of the crystal relatively to another. And when you release the stress, it remains in this particular configuration. It does not relax back to here. So the question is, can you calculate when this happens, in which directions and in which planes it will happen? If you apply a stress, if you know the material, if you know the density of the atoms, the type of bonding, can you predict where, when, and how it will happen, what will be the magnitude of the plastic deformation, etc. So for that reason, for a given material, you can define a slip plane and a slip direction. So you can calculate what is the probability that this slip will happen in a certain direction or in a certain plane. And what we will do is that first we will try to calculate, can we predict what the shear strength of the material will be? In other words, if you do know the configuration of the atoms within the crystal, can you calculate and predict when this plastic deformation will happen? When do you transition from something that is elastically to completely permanently and plastically deformed?